Chapter 26, Direct Current Circuits. Probably one of the easiest chapters. Three resistors of resistances are connected in series. Obviously what you do for resistors in series is you just add them up. So 1 plus 3 plus 5 is 9. Three resistors in parallel are connected. Parallel, the inverses add up. So find the equivalent resistance. So one thing I like to do in the calculator is open brackets and then put an inverse. And then for each of these, 1, 3, 5, I just plug in inverse. It saves a lot of time for me. So 1 inverse plus 3 inverse plus 5 inverse. And then this whole thing will get you the actual answer. What is the current from A to B? Well, over here, they ask for this one. So current, since you don't have any voltages, you can't work with the voltage loop rule. But you can work with one of other junction rule, where current goes in or out, it's additive. So you can go either this side or this side. Since you don't know the current here or here, you can find it out obviously, but it's an extra step. It's easier to work with here and here. So it says from A to B, but from here to here you're doing B to A, so you just do negative of that. So 0.920 and 2 here, so over here it's 2.92. But then that's B to A, so inverse of that minus 2.92 ampere. Applying Kirchhoff's loop rule. So this is the one where you work with voltages. So find the resistance X, and the values you are given are around this loop. Now the loop rule states that the net voltage around the whole circuit, or around one loop, is equal to 0. So if the current is going with the resistor, or resistor doesn't have direction, but if you choose one arbitrary direction, and then if the current is going with it, then it's positive, otherwise it's negative. Or it can be the opposite, because it's going to be released. But you have to be consistent. 0.45 times 2, this direction, it's with it, plus 0.505 times 4, and then as you go here, it's opposite the current, so minus 1.5x. Put in your calculator this over 1.5 and you should get the answer. 1.946666, which is 1.95. Basic question 3. A galvanometer has a coil resistance RC and F full scale deflection, current I full scale. It is to be converted to an ammeter. What is the shunt resistance required? So, as you know, an ammeter, we place it in series with the circuit. So this is in series, ammeter. And in order for it to not be affecting the actual circuit, you make it parallel. Or actually, like inside the ammeter, you have a whole circuit, and here you have a small resistor, and then here you have the large resistor. This is the shunt, and this is the actual coil, or it's the one that lets the current pass. So as you can see, this is a parallel circuit, and you use it to calculate what we have in these questions. So you have a parallel circuit inside the ammeter, not in the actual outside. And then you have that. And then this is parallel, so the voltages are equal. V equals V. And this is the coil. And this is IFS. And this is IA. So IA is total, IFS is for the coil. And this is our shunt. Resistance of shunt. There is no name for over here for the I, so you can leave it blank. Now we know that the voltages are equal across these points, so V is equal to IR. So for this one above, for the shunt, R shunt IA minus IFS, because junction rule. You have this IA, and it splits into two, IFS and the actual over there. So this is equal to the voltage on the other side, which is IFS, into RC. And then to calculate R shunt, you just divide by IA minus IFS, and then you get this. So if you forget the formula during the exam, you can just say, oh, it's parallel, so you can derive it. Let's do an application on that, which is 4A. So you have parallel. An ammeter of 48.5. It doesn't really matter. You don't have to. Well, you have to, I guess. 48.5 resistance gives a full-scale deflection for 3 milliamperes. So this is 3 milliamperes. What must the meter have added to give a full-scale deflection for 100 milliamperes? So this is 100 milliamperes. So they want the R shunt. So you know that IR is equal to IR for the upper shunt and the lower coil. So you know that R shunt is equal to I at that, which is IA minus IFS, into IFS and RC. So you just sub in values. So IFS is 3. You can the bottom is also milliamperes, so you don't have to convert. And then R shunt is 48.5, and then IA minus IFS is 100 minus 3. Now let me take the calculator out here, and 3 times 48.5 over 100 minus 3, it's 1.5. So R shunt is 1.5. That's what you need to add. There you go, in parallel, obviously, as you saw the diagram. Now, next part B, a galvanometer. It is to be converted to a voltmeter of FST, this amount of voltage. Find the resistor required. So, a voltmeter, as you know, if you have a circuit like this, with this here, and this is a battery, to measure the voltage, you connect it in parallel. So, inside the actual voltmeter now, it becomes in series. So you have these 2 points, and then you have the RC, the initial one which was there, and now you have to add the resistor for it to be a voltmeter, which is R, what it was before shunt, but now you just label it RS. So you have a current IFS, which is constant throughout the whole thing. So the voltage is equal to I RT. RT is an R total, and R total is just the sum of the resistors because it's in series. So IFS into RC plus RS, and that's the formula for it. And then if you want to get one or the other, you just do algebra. So you're given this. So 16 is equal to, what was it? V equals IR. So what's AI? 2 times 10 power minus 3. And then R is 20 plus R, because there are 2 resistors. Anytime you hear voltmeter, you can just quickly think of it. 20 plus R. So now you do the math. 16 over 2 times 10 power minus 3, and then minus 20. And you get the answer to be 7,980 ohms, which is a large amount of resistance compared to the 20. This is so you don't disrupt the circuit. So 7,980 ohms. And that's pretty much it for galvanometer and ammeter. There's no more questions about it. In the RC circuits, give the formula for current and charge while charging and discharging. Their formulas, you memorize them, but I'll just give a quick overview. If you don't want, you can just skip ahead to part B. Q equals this. So while charging, you're starting with 0 charge, and then you end up with Q final. So if you look at this equation, as time becomes very, very big, this becomes nearly 0. So it's just QF into 1. So that's why that's a formula like that. That's the only one is where it's 1 minus C. And then while charging, the current, it initially flows smoothly because it barely has any theoretical resistance in a sort. So barely, it just moves normally. But then as charge starts building up, it gets harder and harder to move. That's why the current curve is like this. And that is the shape of E minus, of, like, if you imagine the graph E minus X, the shape is like that. That's how you can remember it. And then while discharging, initially you have a charge Q0, and then just goes like that. So that's why like that. So E minus X again. The plot is like that. And then also current I0, it flows down like an exponential curve, decrease. So let's just apply. A resistance is connected in series with capacitor, so you know it's a RC, and the battery with EMF. Before the switch is closed, the capacitor is uncharged, so this means it's charging. Find the time constant is just RC, so 12 times 2, the mega and micro cancel out, so it's 24 seconds. What is the current at T0 when the switch is closed? When the switch is closed, the capacitor is uncharged, which means current just flows through it, so it doesn't really affect it in any way. So I is equal to V over R, or in this case V is this epsilon, which implies the EMF. So 12 over 12 mega ohm, which is times 10 power minus 6, which is microampere. Find the final charge in the capacitor. Easy. So Q over V is equal to C. That's a capacitance formula. So C is 2 times 10 power minus 6. V is 12. So 2 times 12 is 24. 24 microcoulomb. B6, a resistor with resistance 12 mega ohms connected series with capacitor with capacitance 2 microfarad and battery 12 volts. So it's connected in series, so you know it's RC circuit. Before the switch is closed, the capacitor is uncharged. So again, you have it's charging. So calculate the current at one time constant. So current is I0 e power minus t over time constant, which is RC. At one time constant, so this is RC again, so this whole thing is 1. So the answer is I0 over E, where I0 is V over R. So 12 over 12 times 10 power 6 mega, and then over E. So it's basically 1 over E times 10 power minus 6 micro. So 0.4 microampere approximately. Calculate the charge at one time constant. Again, it's charging, so use this formula at one time constant. So Q final is equal to Q final 1 minus 1 over E. This is the E at one time constant. So what's Q final again? It's 12. Sorry, not this. It's C equals Q over V. You have 12 and you have this, so multiply each other, and you get 24 microcoulomb. That's the Q final, and then 1 minus 1 over E. This is the answer to part B. Yep. B7, 4 resistors are shown. What's the equivalent resistance between A and C? Resistors in series, you can just add them up. So here, R1 plus R2, so 3 plus 4. And then you have to add this, the equivalent resistance of that. So there's a simple way, it's not simple, but it's what you can do on your calculator easily. You put open parentheses, put it to the power of minus 1 with one click of a button. Then R3 and R4 is 24 inverse, click the button again, plus 12 inverse. And you should get your answer. You just add that, that's the total. Find the current through R3. So R equivalent was 15. Now what's R3? This one here. So we know that the voltage is the same for both of these, and we know that this is the equivalent resistance. So what's the current total between A and C? You do V over R. So this over 1.5, or over 15, sorry, V over R, you get 1.5. I'm basing it off of that, the calculation. So you get the current to be 1.5. So the current over here plus the current over here is equal to 1.5. And you know that the voltages are the same between this because they're parallel branches. So you do V is equal to V. So IR, I3, R3 is equal to I4, R4. What's I3? You don't know, you need to find it, so take it as X. R3 is 24, is equal to I4. Do you know what it is? No, but you know that this and this, the current in R3 and current in R4 add up to 1.5, so you can just do 1.5 minus X, and then R4 is 12. So then you put in your calculator, you do some simple algebra, and you should end up with 0.5. The current in a loop circuit, so it's a loop, has a resistor R1, is 4 amperes. So when it's R1 here, it was 4 amperes. And then you have some sort of voltage source that's constant, supplies a constant voltage. The current is reduced to 3 amperes when an additional resistor R2 is added in series. So when this is added, R2, you get 3 amperes, it's reduced. So you still have that same voltage source. How do you play it? You do V equals V, the voltages, and then V is what? IR. So initially it was R1 times 4, or IR, so I, which is 4 times R1, is equal to V again, which is IR. What's I? It's 3 amperes. And what's R total? It's R1 plus R2, which is 2.5. Put it in your calculator. So 4x is equal to 3x plus 7.5, and x is 7.5. A battery with an EMF of 15 volts and internal resistance 0.8 ohms is connected across a load resistor R. If the current is 2.5, find the power dissipated in R. So simple diagram is this. Where this is the battery, and if the current of circuit is 2.5, and what's the load resistor R, and the power dissipated in R. So P is equal to IV, or it's equal to I squared R. Since you don't know R of the resistor, you use this IV formula. So P for the resistor is I, which is 2.5, and then you need to find the voltage across the resistor itself. You know that the total is 15, and you know the R of internal resistance. So 15 minus 0.8 times 2.5, because 0.8 and 2.5 squared, because it's I squared R, to get the power through the actual internal resistance, and then 15 minus that is you get the power through R. Put that in your calculator and you should get the answer. Yeah. The current in a circuit is quadrupled by connecting a 600 resistor in parallel with the resistance R of the circuit. Calculate the resistance R. Okay. So you know this is 600 resistor parallel with the resistance R. Circuit is quadrupled. So voltage is the same. So this voltage supplied is the same. So V is equal to initial I times R, and R you don't know because it was initially, and it was equal to, the current was quadrupled, so 4I, and there is RT, so RT, and that's the total resistance, and this is parallel, so you do the open brackets inverse, R inverse plus 600 inverse. I and I cancel, you put in the calculator and solve algebraically, and you get the answer to be 1.8 thousand ohms, or just 1800. Three resistors, each having resistance R3, are connected as in the figure. Each can dissipate a maximum power of 48 watts without excessively being heated. So, you know that P is equal to IV, or that, no, you use that later on, but a maximum power of 48 watts without being excessively heated. So P is equal to I squared R. And since these R are constants, you look towards which one will have the highest I. It's going to be this one, because this is, the I is split in this equally. So this one emits I squared R. So the maximum power that the network can dissipate is 48 watts. And over here, this is I squared R, so 48 equals I squared R. R is 3. So 48 is 16, so I is 4. And over here, R and R, this resistor and this resistor are equal, or they're identical. So it will split it evenly. So if there was 4 ampere here, there will be 2 ampere here and 2 ampere here. And then you use P equals I squared R for this, and P equals I squared R for this. So the total power dissipated from this whole network is the 48 plus I squared R for here, so 2 squared times 3, and then 2 squared times 3 for this as well. So this is 12, and this is 12, so 48 plus 24, which is 72, and that is the answer. Basic 11. Initially, for the circuit shown, the switch S is open and the capacitor of 20 microfarads has a voltage of 120 volts and R equals 3 mega ohms. Switch is closed at time t equals 0. Calculate the charge in the capacitor when the current in the circuit is 35 microamperes. So for this, you have to see, is it charging or is it discharging? So the switch is open and the capacitance has a voltage, which means it's charged initially. And then when you close the switch, the charge dissipates into the resistor and it gets used. So this is a discharging RC circuit. Use the formula from a few questions ago. Calculate the charge on the capacitor. So the charge was Q, or rather Q is equal to Q0 e power minus t over RC, and current was I is equal to I0, and what's I0? It's QC over RC, Q0 over RC e power minus t over RC. This is the equation which is also equal to I0. Now, if you notice something, this initial part over here is almost exactly identical to this part here. So you can simplify the equation to be I is equal to Q over RC. And now that you did that, let's simplify the equation. So when the circuit is 35 microamperes, so Q is equal to 35 micro times R, which is 3 mega, so this cancels, times C, which is 20 micro. Now you just multiply this and then apply the micro for the unit. You get it to be 20 times 30 is 60. 60 times 35 is 2100, and that is exactly what you get over there. Find the capacitor voltage when the time is equal to 75 seconds. So, capacitor voltage is Q is equal to Q0 e power minus t over RC. It's t over RC. It's e power minus t over RC for all formulas except for charging and the charge while charging. So you have this equation. How do you get the voltage? If you divide both sides by capacitance over C, you'll notice that this is the voltage and this is the voltage at any given time, t. So V final, you can just keep it as Q0 over C, e power minus t over RC. So, actually you have the given, that's 120 there. You have the voltage, you don't have to do Q over RC, or Q over C. So 120 e power minus 75 over RC. Now R is this, C is this, mega and micro cancel out, 20 times 3 over 60. And then put in your calculator, you should get 34.4 volts. And that's pretty much it for chapter 26. On to Nakul.
Alright guys, let's start the revision for the electricity chapter 27. Question 1, part A. An electron of charge 1.6 times 10 to the minus 19 coulombs moves with the speed of 4 times 10 to the 6 meters per second along the x-axis. It enters a region where there is a magnetic field of magnitude 1.5 Tesla, directed at an angle of 30 degrees to the x-axis and lying in the xy plane. Find the magnitude and direction of the magnetic force on the electron. So I'll give you guys a few seconds. You can solve and then we'll check together. Alright, let's check. They want the magnitude and the direction. The easiest thing is to find the direction. So let's just write direction. Alright. So for this, we have to use the right hand rule. And to help us, I have given us the diagram here, the x, y, and z axes. Right, so we have to use our thumb, and our thumb is basically the velocity, right? We have to point it along the direction at which the velocity is moving. Our index finger has to point upwards, that's the magnetic field, and the perpendicular thing, our middle finger, is the force. So that shows us where the force is. So if I put my thumb to the right, if I put my index finger up, where does my middle finger of my right hand, where does it naturally point? It naturally points towards me, right? And towards me is the positive z axis. Anything I've drawn here is the positive, right? This is the origin. But one thing to consider, we're looking at an electron here, electron. Let's think of it this way. We have a capacitor, negatively charged, positively charged, right? The field goes from the negative to the positive, right? But if I have an electron, what does it experience? It experiences a force opposite because of the charge, right? So if I erase all this, and if we consider that it's an electron, the force direction is in fact reversed, so it's the negative z axis, or into the page. The page being, the plane in front of you. And symbol wise, it is represented like this, across. Right? Now let's look at the magnitude. This is quite simple. You have to use the formula. The formula to find the magnetic force on a charged particle is F equals QVB sine theta, where theta is the angle between the velocity of the particle and the magnetic field. For magnitude, we always we take the absolute value, so 1.6 times 10 to the power minus 19 by the velocity 4 times 10 to the 6 times the magnetic field times sine. What's the angle here? It is 30 degrees, and we should get, once we solve everything, 4.8 times 10 to the power minus 13 newtons. I'll give you guys a few seconds to check and then we move on. Alright, let's move on. B. We have a disk of radius 1.5 centimeters. It's found in a region of uniform magnetic field of 4 Tesla, making an angle of 37 degrees with the plane of the disk. Calculate the magnetic flux to the disk. So I'll give you guys a few seconds to solve and then we check together. Alright, let's check. Right? let me just draw one more line and then we're good. Okay, let's draw a blue line like this, right? Okay, so this is our A. This is the area vector. It is always perpendicular to the plane of the surface, and this is our magnetic field. The formula for flux, the magnetic flux being, so phi B is B, which is the magnetic flux field, times the area cosine theta, where theta is in fact the angle between the area vector and the magnetic field vector. But they told us that this angle is 30. So do we put cosine 30 or what do we put? No, we put cosine 60 because we're looking for the angle between the area vector and the magnetic field. So we substitute, and when we substitute we should get 1.7 times 10 to the power of minus 3 Weber. And obviously when we're looking for the area we do pi r squared because it's a ring or a circle, and obviously r has to be in meters. So we should get 1.7 times 10 to the power of minus 3 Weber. Alright, let's move on to question 2. We have a proton of mass 1.67 times 10 to the minus 27 kilograms and charge 1.6 times 10 to the minus 19 coulombs, moving with a certain speed. It enters the region of uniform magnetic field perpendicular to its direction of motion and of magnitude 0.8 Tesla. Find the radius of the trajectory. I'll give you guys a few seconds to solve and then we check together. Alright, so this is our proton. It's moving to the right. It experiences, let's say, a magnetic field downwards. So using the right hand rule, we see that the magnetic force is actually out of the page. I can't draw a 3D diagram obviously, so you will have to imagine, this is a right angle here and this is another right angle here. So in fact it has to move like this. If I continually find the force, it has to move in circles. So there exists a radius, right? So we have to find a formula for this. Well, if we think about it, what is the magnetic force? It is QVB. Now why I'm not putting the sine theta? Because sine 90 is 1 and it is moving in circles. This is UCM and the centripetal force is mv squared over r. What are we looking for? We're looking for r, but we can divide by v. So in fact our r is, if we cross multiply, we get mv over qb. This is a quick derivation. So when we substitute, we should get 1.67 times 10 to the minus 27. Velocity 2.5 times to 5 over the charge 1.6. They may not give you the charge. This is a constant and must be memorized. And the magnetic field is 0.8, and we should get 3.26 times 10 to the power of minus 3. The unit here must be meters because this is a distance, it's a radius. So we can immediately use this formula, or you can derive it using setting the forces equal to each other. Alright guys, I'll give you a few seconds and then we'll move on to part B. Alright, let's move on. B. Let's read it. In a velocity selector of crossed electric and magnetic fields. Okay, so we have a velocity selector. We have the magnitude of an electric field is 5 times 10 to the power of 6 volts per meter, and that of a magnetic field is 0.8 Tesla. What is the speed of the particle? Okay, one thing we should know in a velocity selector is that our electric force is equal to our magnetic force. What this means is we should know that Fe is in fact equal to QE and Fb is equal to QVB. The Q's cancel, and when we are looking for, it was velocity I believe, or the speed, V is equal to E over B. Again, this is a formula that you may memorize or you may choose to derive. So when we substitute, E over B, where E is 5 times 10 to the power 6, B was 0.8, giving us 6.25 times 10 to the power of 6 meters per second. So in the velocity selector, the only formula that we actually need to know is this. Velocity selector because we should know that the electric force has to equal the magnetic force, and then we can substitute, and then we can derive a formula. So this is how you solve part B. Number 3 now. A wire carries a steady current of 2.5 amperes. Okay. A straight section of the wire is 0.6 meters long and lies along the x-axis with a uniform magnetic field. B is equal to 2.4 T K, Tesla K. If the current is in the positive x direction, find the magnetic force on the section of the wire. Okay. So I'll just quickly draw the XY diagram to help you guys. Z and this is Y. And I'll give you guys a few seconds and then you can check. Alright. We should always remember the right hand rule. Alright, let's check. So we should know that the current is in the positive x direction. So our thumb points to the right. Okay. We know that the force, where is the force? Okay. The magnetic field is K. K is the positive Z axis, so it should point towards me. So where does my middle finger naturally go? It naturally goes down. So in fact, it's in the negative Y axis. Or, since we're talking about K slash negative J. Now we've gotten that out of the way, we can calculate the magnitude. It's the exact same thing, but in this case, we have the current, we have the length, and we have the magnitude of the magnetic field. It's ILB sine theta, but this time theta is 90, so it's cancelled, it's 1. So it's 2.5, 0.6, 2.4. We should get negative 3.6. Why is it negative? Because it's in the negative y axis, so it's downwards, newtons. And that's the answer. Because in this they're asking us for the force, but the force is the vector, so we must always simplify the show the magnitude and the direction, negative G. Give you guys a few seconds and then we move on to part B. Alright, part B. Let's read it. We have a circular coil 6 centimeters in radius with 60 turns of wire, each carrying a current of 5 amperes. The coil is in a uniform magnetic field with magnitude 4 Tesla, making an angle of 60 degrees with the plane of the coil. Find the torque on the coil. I'll give you guys a few seconds and then we check together. Alright, let's check together. So let's just draw this. We have a coil, so basically it's a bunch of circles together like this, like this, like this. Or actually not, let's make a better drawing. This is not a good drawing. This, and then we have like this, like this, like this. But our radius is obviously, our length is not much bigger than the radius. So let's say like this, right? And then this is our area vector pointing outwards, right? And then this is our magnetic field. Perfect. This is our center. So this is the radius. This is 60 degrees. This is B. This is A. And they're asking us for the torque on the coil. So we should know that the formula is NIAB sine alpha. It's a very long formula. So let's see. N is the number of turns, which was, sorry about that, 60. I is 5. A is the area, so 0.06 squared times pi. B is the magnetic field, being 4 Tesla. But what's sine alpha? Sine what? Do we do sine 60, sine 180? What do we do? Well, the alpha is obviously has to be the angle between the area vector and the magnetic field. We have 60 being the angle between B and R, so obviously the other angle would be sine 30, giving us an answer of 6.79. But what is the unit of torque? Well, we should know that torque is in fact force times distance, right? It's the work. And force times distance is Newton times meter. So this is our unit, 6.79 Newton meter. Let's check and then we move on to the next question. Alright guys, number 4. Part A. The Earth's magnetic field at a certain place is 3.2 times 10 to the minus 5 Tesla at an angle of 30 degrees with the horizontal. Calculate the flux through the horizontal ceiling of a rectangular room 6 by 8 meters. Okay. Give you guys a few seconds. I've drawn a little diagram here that illustrates the situation. And you guys can solve and we'll check together. Alright, let's check. Magnetic flux is BA cosine theta. So B is given to be a 3.2 10 minus 5. A is very easy. It's a rectangle, so it's 8 by 6, 48. But what's our cosine theta? Cosine blank. 30 is the angle between the magnetic flux and the horizontal, so it's obviously 60 degrees because we always look at the angle between B and A. And we should get 7.68 10 to the minus 4. And the unit we use for flux is Weber, WB. That's A. A is very straightforward. B. A particle with charge negative 6 times 10 to the power minus 8 is moving with instantaneous velocity of 4.5 times 10 to the power 4 meters per second J. Find the force exerted on the particle by a magnetic field 5 Tesla K. This has IJK, so I'll just draw the three-dimensional plane that helps you visualize it better, and then I'll give you guys a few seconds. Alright, so let's think about it, right? I'll draw it again so we don't have to go back and forth. Y and Z, right? So the velocity is upwards, so thumb facing up. The field is into me, it's positive Z, so our right hand, the middle finger naturally goes to the right. So you would say the force is positive X direction, right? Wrong. Because it's a negative particle, the force goes opposite, so it's actually in the negative X direction, so negative I. So F equals QVB sine theta, where you can substitute all the values. Obviously, we can use Q to be negative because anyways our answer is in negative I. And when we substitute, we should get negative 0.0135 I. And obviously newtons. So negative I because our force is in the negative X direction, and newtons because it's a force. Give you guys a few seconds and then move on. Alright, number 5, part A. Electron experiences a magnetic force of magnitude 6.7 times 10 to the power minus 15 newtons when moving at an angle of 37 degrees with respect to a magnetic field of magnitude 3.5 times 10 to the minus 3 Tesla. What is the speed of the electron? Again, a simple question. Give you guys a few seconds and then we'll check together. Alright, let's check. So we want the speed, or V. We have the force, so it's obviously F equals QVB over sine theta, or QB sine theta. We have to substitute, so 6.7 minus 15. Q is obviously 1.6. We take the absolute value. B is 3.5 times 10 to the power minus 3. And the angle is 37, so sine 37. Yes, sine 37. And then when we substitute, we should get 1.93 10 power 7 meters per second. So most questions are straightforward applications of the base formula, which is F equals QVB sine theta. And then you have to play around with the variables. Alright, part B. We have a circular area with radius 5 centimeters lying in the xy plane. Find the magnitude of the magnetic flux through the circle due to a uniform magnetic field of magnitude 0.6 Tesla in the positive z direction. Give you guys a few seconds and then check together. Alright, let's check together. So we have a circle in the xy plane. So this is the x, this is the y, this is the z. So any magnetic field will obviously be perpendicular. So the angle between the area vector and this is 0. So magnetic flux is BA sine theta, or wait, no, it's BA cosine theta, I'm sorry. But since the angle is 90, it's 1, so cancel that out. We just have B times A. So it's 0.05 squared pi r squared into what's the negative 0.6. In the calculator, we should get 4.71 10 to the minus 3 Webers. Alright. Let's move on to part 6. Number 6. Excuse me. A singly charged ion moving with speed of 3.9 times 10 to the power 5 meters per second enters a region of uniform magnetic field of magnitude 0.52 Tesla, perpendicular to the direction of motion of the ion, and describes a circular arc of radius 50 centimeters. What is the mass of the ion? This actually, they use this technique in fact, of putting a force perpendicular to the ion to make it move in circles to calculate the mass, because because the formula gives you the mass. So this is a method in which you can measure the mass of an ion. Alright, let's check together. So if we remember, we said before that QVB sine theta is 0 anyway, or is 1, sorry. QVB equals mv squared over r, and we're looking for m, so the v cancels with the v. M in fact is QBR over V. So it's let's see, a singly charged ion. Okay. So the velocity is 3.9 10 power 5 0.52 0.5 meters, and the charge is 1.6 times 10 to the power minus 19 because it's singly charged. They haven't mentioned otherwise. And our mass is in fact a very small mass of 1.07 times 10 to the power minus 25 kilograms. So you can just, an easy way whenever you're dealing with the uniform circular motion is set the forces equal, and then you can look for whatever you're looking for, right? Alright, B. You have a horizontal rod 35 centimeters long, is mounted on a balance and carries a current. At the location of the rod, a uniform horizontal magnetic field has magnitude of 0.02 Tesla and direction perpendicular to the rod. The magnetic force on the rod is measured by the balance and found to be 0.21 newtons. Find the current. Okay. So they've given us the force, they've given us the length, and they've given us B. They're asking us for I. So, well, since we know that, it's the, what do we say? It is, it's a force on a moving current in a wire. So it's F equals ILB sine theta. Sine theta as usual is 1. We're looking for I. So it's F over LB. And when we substitute, we should get 30.0 amperes. So it's a moving current of 30 amperes that causes a force of that much magnitude to be given. Alright, let's move on to the next question. Alright guys, let's move on to question 7. A wire having a mass per unit length of 0.6 grams per centimeter carries a 3 ampere current horizontally to the north. What is the magnitude and direction of the minimum magnetic field needed to lift the wire vertically upward? So I've done a quick circuit here, diagram here. We have a wire, we have the force upwards and the weight downwards. Obviously this is not like an accurate drawing because I can't draw it's perfectly perpendicular. It seems like the force is to the west while it's actually upwards. So this is actually what happens in maglev trains, magnetic levitation trains. Obviously you have much bigger scales there, but this is a very simplified explanation of what happens. So let's think about first the direction, right? So our thumb goes to the right, our middle finger goes vertically upwards, and then naturally our index finger points into the page or to the west direction. So our direction here is the west. the magnitude, we should know that F is equal to ILB, and in this case also mg, right? So B in fact is equal to m over L, because we have m over L, mass per unit length, times g over I. I've done this very on purpose. I've done this, right? So I have 0.6 grams per centimeter. I multiply this by 1000 grams, 1 kg. I want to get rid of the units. 100 centimeters and 1 meter. So the units cancel. This becomes 10. So in fact it's 0.6 over 10 times 9.8 over 3. That gives me a magnetic field of 1. Oh, sorry. Let's erase that. 0.196 Teslas. So magnetic field should be 0.196 Teslas to the west to have a force that's equivalent in magnitude to the weight to lift our wire vertically upwards. Because this is Newton's first law, right? Balanced forces will have no effect, like the body will be at rest. Question 8, part A. Fine, we have alpha particles of a given charge 2 plus 2 of electron. Mass is given. Accelerated in a cyclotron to a final orbit radius of 0.8 meters. The magnetic field is 0.6 Tesla. We have to find the period. So I'll give you guys a few seconds and then we check together. Alright, let's check together. So we want the period of circular motion. First, you should know that the force is equal to QVB. Sine theta, we don't care about, it's perpendicular. And it's centripetal, so mv squared over r. The v's cancel. We should get that v is equal to QBR over m. But we should know that v is equal to r omega is equal to QBR over m. The r's can cancel. But we should also know that omega is 2 pi over t, or the period, right? That's QB over m. Simplifying for t, we should get that t is equal to 2 pi m over QB. When we simplify 2 pi, the mass, 2 times 1.6 minus 19 times the magnetic field 0.6. The 2's cancel. If you get that the period is 2.19 times 10 to the power of minus 7 seconds. Right? So the alpha particles, they move every time around a circle. It takes them 2.19 times 10 to the power of minus 7 seconds. So what we did here was we equated the forces, a centripetal force to the magnetic force, found an expression in terms of V, found one in terms of omega, and then using that we found the period. Let's find part B, the magnitude of the centripetal acceleration. Well, we should know that alpha, or the centripetal acceleration, is r omega squared, So that's 2 pi over t, all of that squared, times r. 4 pi squared r over t squared. R was 0.8 I believe, and we have t from before, and we should get 6.59 times 10 to the power of 14, and since this acceleration meters per second squared. I'll give you guys a few seconds and then we'll check. Alright, let's move on to question 9. We have a uniform magnetic field of magnitude 0.6 Tesla in the positive z direction, which is present in a region of space. We have a uniform electric field as well. An electron projected with initial velocity v0 is in the positive x direction. It traverses the region with zero deflection. What is the electric field vector? So first thing we should know, electron is very light, gravity is negligible, so we don't need to care about the weight as a force. Let's think of the electron this way. It's moving along in the x direction, in the positive x direction, right? And now X and we have the magnetic field in the positive Z direction, so out of the page, right? So you point the middle finger to the thumb to the right, index finger towards you. The natural force is upwards, but it's an electron, right? Oh wait, sorry, the force is actually downwards, so it's an electron, so it makes everything the opposite. So the magnetic force is upwards. Let's go over that again. Thumb to the right, middle finger towards you, the index finger towards you, middle finger naturally goes down, but it's an electron, so it reverses everything. The magnetic force is upwards. Naturally the electric force has to go downwards, and since it's an electron, E is upwards. The direction of the electric field vector is upwards. Now all I have to do is find the magnitude. We knew that V is equal to E over B, so E is equal to VB. So 0.6 times 2.5 10 to the 4, giving us 15 times 10 to the power of 3. A unit could be volts per meter or newtons per coulomb, and it's obviously upwards. So we can, to find the direction, we have to do a little bit of thinking, but we can get it in the end. Because a few seconds and then we move on. One tip always to remember is it's an electron, so obviously the directions are always reversed. Number 10. Give you guys a few seconds to solve and then we check together. Alright, so we have a 12 meter length wire carrying a current of 5.6 amperes lying on a horizontal table with a rectangular top with the given dimensions. The ends of a wire are connected to the opposite ends, so here and here, right? So we want the magnitude of the magnetic force given the magnetic field. So it's obviously F is equal to ILB. Sine theta is obviously 90 because it's present, right? It's vertical and our current is moving horizontally, so it's sine theta, but theta is 90, so we get rid of it. So we know I is 5.6. We know the magnetic field, but we don't know the L. Do we use 12? What do we use? But we should think about it this way. We only use the L on which there is a current, on which there is a magnetic field acting. We do have a current here and we do have a current here, but they're parallel to the magnetic field. The magnetic field in fact is upwards, vertically upwards. So since they're parallel, sine theta is 0, so sine theta is 0, so there's no force. So all we have, the only section of a wire that we have force on is the diagonal. So we do the square root of 1.8 squared plus 2.4 squared, and when we solve all that we should get 4.2 newtons. So basically we take the length of the diagonal of the rectangle only because that's the only section of the wire on which there is a force occurring. Nowhere else do we have a force. Give you guys a few seconds and then we move on to the last question of chapter 27. Alright, let's move on. 11 part A. We have a circular coil of 250 turns in diameter 2.5 centimeters carrying a current of 4.5 amperes. It is placed in a magnetic field of 0.4 Tesla with the plane of coil making an angle of 37 degrees of the magnetic field. Find the torque. We're always repeating ourselves. we had a simpler question very similar to this. So it's torque equals NIAB sine alpha, number of turns 250, current 4.5, area, it's the radius square times pi, so pi times 1.25 half over 100, all of that squared into B, 0.4. Now the plane of the coil making an angle of 37 with the magnetic field. So the coil is like this, the magnetic field is like this, 37 degrees. But we need to find the angle it makes with the area vector, which is perpendicular. So that's 53 degrees. Yes. So that's sine 53 degrees, giving us a total of 0.176. But what's the unit? Newton meter, because it's force times distance. So that's 11E. B. Sorry about that. Yes. A particle of charge -5 microcoulombs and mass 3.5 times 10 to the 12 minus 12 kilograms has velocity 4 kilometers per second as it enters a region of uniform magnetic field. Particle is observed to travel a circular path. So immediately we should think of UCM, centripetal force. Radius 7.5. What is the magnitude of the magnetic field? Okay. Very simple. We have to do F equals QVB, which equals mv squared over r squared. That cancels. We're looking for the magnetic field, so B is equal to mv over qr. We substitute, it was 4 kilometers, so it's 4 times 10 to the power of 3, because we have to make it meters per second. 3.5 times 10 to the power of 12. It was, I believe, 6 10 to the minus 6, because it was micro. The radius was, oh, it's 5, sorry, 5, and the radius was 7.5 over 100. So we finally get 0.0373 Tesla. So this was our magnitude of the magnetic field. So with this, we're done with the electricity portion of the physics periodic that's coming on week 6. Hopefully you guys, study well and get good grades. So good luck for the mechanics portion. Thank you.